Hi everybody, in the last video we talked about an ANOVA very briefly, just introduced the basic idea and why we need to do an ANOVA sometimes, why we can't just do a series of t-tests for example, or shouldn't do a series of t-tests. Now in this video I'm going to introduce what is called the one-way ANOVA. It's a specific type of ANOVA, and we'll talk about some of the assumptions of this test and what the hypotheses look like. So this is sort of all of the stuff that you need to be able to do and set up before you start calculating your ANOVA. We'll get to the calculations eventually though. Okay, so there are several different types of ANOVA. For example, some of them use more than one independent variable. Some of them are repeated measures kinds of ANOVA, things like that. We're just going to talk about, for the next several videos, the one-way ANOVA. So we'll work our way all through that. A one-way ANOVA includes only one independent variable, which is categorical or ordinal, but it has essentially two or more levels of that independent variable, and then a dependent variable that is continuous. And generally it's at least got interval properties. It would be a little bit weird to use only ordinal properties on a dependent variable. Now there are some exceptions to this. For example, if you had a categorical variable that is dependent and you had a continuous independent variable, you can still technically do an ANOVA in that way. It's just a little maybe confusing, and there may be some other more appropriate methods. So if you're not sure, please consult with somebody with a PhD and work this out. Like me, you can talk to me about that as well. Okay, so here's one example, however, of a one-way ANOVA. So let's imagine that we've got an independent variable. In this case, we've got three levels of the independent variable, or what that is the independent variable can take on three values. And our independent variable is some kind of method of treatment. You've got method 1, you've got method 2, and then you've got a control group in this particular case. So in other words, everybody gets randomly assigned to either the control group, the method 2 group, or the method 1 group. And then we want to see how they measure on their dependent variable. And it could be any kind of thing. Let's say it's depression symptoms, for example. Now, of course, with any statistical test, we need to be aware of the assumptions that the test makes. In other words, it's the things that the statistical test assumes to be true. And it can't tell if it is true. That's entirely up to the researcher to determine whether these things are true. Because if they're not true, the test that we're using may be making a mistake here. So we need to be aware of these. Now, luckily, the ANOVA, the one-way ANOVA's assumptions are very similar to those of the independent samples t-test. So we'll talk about those, of course. A normally distributed dependent variable, in other words, the dependent variable, as long as that is the continuous measure that you're using, should be relatively normally distributed. Now, of course, there are formal tests to determine whether it is normally distributed, a little beyond what we're going to do here. We also assume, or this test assumes, that group membership was randomly assigned. Now that is not always possible, right? I can't always randomly assign people to one of my treatment groups or my control group. In some cases, for example, maybe the independent variable would be something like race. I want to see if people of different races have different, we'll say, income levels, for example, on average, or maybe different education levels on average. Because I can't randomly assign race, this may be an assumption that is violated. So even in cases where it is violated, however, as long as they are independent of each other, that's probably okay. That's about as good as you can get, because there are some things we simply cannot randomly assign. And it also assumes that each group's variance is relatively close to the other group's variances. One quick way to look at that is you can calculate the standard deviations of each group on that dependent variable, and you should see that they're roughly the same. They're not exactly the same usually, but at least they're pretty close to each other and comparable. And of course, just like the independent samples t-test, the one-way ANOVA is robust to violations of these assumptions. That means that if you break one or more of these violations, it's still probably going to make the correct call. However, you want to make sure that you communicate any violations to your audience, try to control for them, try to account for them if nothing else, and proceed with caution. Of course, before proceeding with a test, we need to also be aware of what are the possibilities, what are the possible outcomes, so that we can know which one is best supported by the evidence. These, again, are roughly similar to an independent samples t-test hypotheses, except, of course, they're a little more complicated because now we have three means that we're comparing. So, of course, the null hypothesis is always that there's zero effect of the independent variable on the dependent variable. And so, therefore, in this case, what that would look like is this, right? In other words, if we have 3 groups in this particular example, and in an ANOVA you could have more, what I'm suggesting that is if the group membership has no effect whatsoever on the depression levels, then I expect the mean depression levels of group 1 to be no different from the mean depression levels of group 2 and to be no different from the control group depression levels. Okay, so in other words, what I'm essentially saying is I don't expect the group means to differ at all. Or in other words, the default hypothesis is that the group's means are not going to differ whatsoever. In other words, our independent variable had no influence on the dependent variable. Our manipulation had no effect whatsoever on that dependent variable. So the alternative then gets kind of complicated here. The one way that we can summarize it nicely is to just say there's something wrong with the null hypothesis. There's something untrue about the null hypothesis. So in fact, you can just summarize it in this way, is to say that our alternative is that that's actually not true, right? We got that wrong. Now, of course, what you're really saying is there are lots of actual alternatives here. For example, it could be that none of the group means were similar to each other. In fact, they were all meaningfully different from each other. Maybe group 1 was way lower than the mean of group 2, and group 2 was way lower than the mean of group 3, for example. That would be one possibility. Another one is that only groups 1 and 2's means differed from each other. Or it could be just groups 2 and groups 3. Anyway, you could see where I'm going with this. There are several different alternatives here. It could just be group 1 and group 3 that differed, but group 3 and group 2 didn't differ. And maybe group 1 and group 2 didn't differ, which is difficult to symbolize here, right? Anyway, the idea here is that with 3 means, we've now opened up a world of possibilities as to where these differences lie. Now, that's important for later, however. When just stating the null and alternative hypotheses, you can essentially just use this as the alternative. Now, which of these possibilities is true, we'll figure out here later. I'll show you that in a second. Okay, that's important because essentially the ANOVA comes in 2 stages, and any ANOVA will do this, not simply the one-way ANOVA. The first is called the omnibus test. It's where you decide, do I support the null hypothesis or not? Okay, what'll happen is we essentially compare all the means together simultaneously in one big statistical equation. Then it comes out and says we can support the null or we can't support the null, or we shouldn't support the null perhaps. Okay, and that's called the omnibus test. So it's dealing with several things at once, and these several things it's dealing with, of course, are the mean comparisons all at once. Okay, the means of group 1, 2, group 3 and 2, group 3 and 1, for example, when you have 3 means. Then, once that is completed, if you can reject the null hypothesis, then you move on to stage 2, which is called the post hoc tests. The post hoc tests tell us which of those alternative hypotheses is true. In other words, is it that group 1 is different from group 2, but group 2 is not different from group 3? Is it that group 1 is different from group 3, but neither is different from group 2? Or are they all different from each other? And on and on. It was all of those possible alternatives that the post hoc test checks out. So we have to run a series of things there. We'll cover that, though, once we get to that in due course. And post hoc, of course, is Latin for afterward, or it literally means after this. So you could think of it like that in that translation, is that it comes after the omnibus test. And really, there's no reason to do it unless you have already found statistical significance from the omnibus test. So if you don't find a statistically significant statistic, which is an F value, in the omnibus test, then there's really no reason to move on to the post hoc test because it's not going to give you a different answer than the omnibus test. With a few caveats, there are some slightly more conservative versus more liberal post hoc tests, but generally you shouldn't move on to it if you did not find statistical significance. I'll of course talk quite a bit more about that once we get to the post hoc test section, so that'll be in a few videos in this playlist. All right, let's summarize what we covered in this particular video. A one-way ANOVA has one categorical independent variable with 2 or more levels. And the dependent variable is continuous. Now, as I said, there are some caveats there. You can sometimes switch that around. And the independent variable could have far more than just 2 levels as well, as I've said. They could be ordinal as well. And it's important that we're aware of these assumptions and we clearly state our hypotheses, our null and alternative hypotheses, before we carry out a test. Okay, we'll see what this now looks like in the next video. I'll show you the equation and how we come up with all this. See you then.